To start the examples for the statics and strength review, we will begin this example by calculating the support reactions and draw and label the shear and moment diagram for the given beam. Okay, we're given an overhanging beam with a span of 15 feet and an overhanging of 5 feet. We have a uniformly distributed load on the 15-foot span of 1.6 kips per feet, which we will turn into a resultant force. We have two concentrically placed 8-kip point loads that are 5 feet apart, here and here, and we have a 10-kip point on the end over here on a slope of rise of 4 over a run of 3, which creates a 3-4-5 triangle. The first thing we want to do is change the distributed load into a resultant force, so we can take here the 1.6 kips per foot times the length of the load of 15 feet to get a total of 24 kips. Here we have a free body diagram, and we have a pin at A, so we can put a vertical reaction and a horizontal reaction labeled AX and AY, and at B we'll have a vertical reaction BY at the roller. We have 3 equations and 3 unknowns, and since there's only one unknown in the x direction, we can find it first by summing the forces equal to 0. That's equal to AX minus 3 over 5 times the 10 kip force. So for this, we're going to get that the force AX is going to equal 6 kips going to the right. Okay, and now that we have that, we're going to look at our 2 vertical reactions at AY and BY. So we want to make the moment using the point at A as the point to take our moment so that everything is to the right. We'll take the loads left to right as we sum the moments, with positive being counterclockwise based off the right-hand rule. Our first point is an 8-kip load that is a distance of 8-kip load, a distance of 5 feet away. So because it's pointing downwards, it's negative. So we have minus 8 kips times 5 feet. Next, we'll take a minus 24 kips times the 7.5 foot distance. And then lastly, for the points, we will have the 8-kip load, which is 10 feet away. So minus 8 kips times 10 feet. And then next, we have the reaction at B, so BY times the 15 foot, which is a positive value, so we have a plus BY times 15 feet. And finally, we have the vertical component of the 10 kip force, which will be downward at 20 feet, causing a negative moment. So we have minus 4/5 times 10 kips times the 20 feet. And by doing the algebra here, we see that BY is our only unknown. So we get that BY is equal to 30.67 kips upwards. And next we're going to take the sum of the forces in the y direction to find the other vertical reaction at AY. Going from left to right, we have that AY in the positive direction minus the 8-kip load minus the 24-kip load minus the 8-kip load plus the BY, so the 30.67 kip load, and finally minus the vertical direction part of that 8-kip load, so minus 4/5 times the 10 kip load, and we do the algebra to get AY is equal to 17.33 kips in the upward direction. And that's BY. Okay, now that we've found the reactions, we can place them on the free body diagram and we can draw the shear and moment diagrams. In this case, we have sort of shadowed down some guidelines to go by in our diagrams. And so we'll go by those for our shear. So we'll start with our shear diagram at the pinned reaction. Our shear will start at 0 and immediately go up to the reaction that we found in the prior slide. AY equals to 17.33 kips. So we'll put that here. And we're going to get some scrap paper and take some notes. So keep in mind that one of the relationships we can use is that the area under the load is equal to the change in shear. So delta V. So we'll have this paper for our hand calcs and some notes. So here we're going to find this shear, and so we'll say that in this case, between the shear between point A and the first concentrated load, we'll call that D, at 5 feet away, and we'll have a load that changes in shear. So this will be equal to 1.6 kips per feet times the distance of 5 feet, and it is negative because it goes downward. This is going to be equal to minus 8 kips. So that means we will drop down 8 kips from our 17.33 kips. So our new shear at D will be our 17.33 kips minus our 8. So we'll go down to about 9.33 here. And now we're going to note that the other relationship will be that the slope of the shear at any point is equal to the value of the load. So in our case, the value of the load is a constant 1.6 kips per foot, which means the slope is a constant 1.6 to get down to our point of 9.33 kips. So it's going to be a straight line like the constant of the distributed load from the free body diagram. And now, from here, we're going to note that we have an 8 kip load that is applied directly at point D. So at point D, we'll drop from 9.33 kips minus 8 to get to 1.33 kips here. So we're just going to drop down. And from there, now we want to find the change in shear from point D that we had before to our new point, which we'll call C, and that's going to be equal to the area under the load, like we described. That's going to be minus 1.6 kips per foot times the length of 5 feet, which is again equal to negative 8 kips. So we're going to drop another 8 kips from point D, so that the shear at point C will be equal to the 1.33 kips minus the 8 kips, so we get a negative 6.67 kips. And here we're going to drop down below the axis to a minus 6.67 kips. And note again that the value of the load is equal to the slope of the shear, which in our case is a negative constant 1.6. Right there, there's our straight line. Okay, so now we need to know this distance, and there are several ways to find it out where the line crosses the axis. The simplest way is to realize that the slope of the shear is equal to the value of the load. So if we start off with 1.33 kips, and we're dropping by 1.6 kips per feet, our distance x would simply be the shear divided by the slope. And from that we get a distance of 0.83125 feet. And here we can label the new distance on the shear diagram. Another way would be to do similar triangles, but it will get you the same distance we just found. Okay, now, so at point C, we have another point load of 8 kips that we want to drop down from negative 6.7, which is now equal minus the 8 kips. So now we have negative 14.67. Now we have this change in shear from C to B. This will be equal again to the area under the load, which is minus 1.6 kips per foot times the length of 5 feet. Again, this will get us another negative 8 kips. On the shear diagram, this will drop us from negative 14.67 kips. So right here, again, down another 8, so we'll get negative 14.67 minus 8 to get a negative 22.67 kips. And again, we have a constant value, so the slope is going to drop by a slope of negative 1.6. It's going to be a line. And then, right here, constant. So from here, now we have a 30.67 kip reaction at point B, so we're going to go up that 30.67 kips. And when we add that to the negative 22.67, we get the new shear is at 8 kips with no slope. We just go straight up and straight up from there. And finally, we take the vertical component of the 10 kip force, which is 4/5, which ends us being at 8 kips downwards. We then get our shear from there back to 0, because prior to that there was nothing, so we could just go straight across to the last piece and go down another 8 kips to 0. Okay, so now for that we're going to use a similar technique, and we're going to draw our moment diagram. And the first thing to keep in mind is that the area under the shear diagram is equal to the change in the moment diagram. So in this case, our first area here is a trapezoid. So we're going to find the trapezoidal area between point A and D. So we can say that the change in moment between point A and D is equal to 1/2 the parallel sides. So this is 17.33 plus 9.33 times the distance between them, which is 5 feet. And this would give us a change in moment of 66.65 kip feet. So we'll start at 0, and we're going to go up to 66.65 kip feet. And now that we want to find the second relationship between the shear and moment, and that is the slope of the moment diagram is equal to the value of the shear at any point. So here we're going to show these slopes. So if we note that the value of the shear between points A and D is positive, we know that the slope of the moment here is positive. It's steeper on one end than the other, so we're going to lightly draw in these slopes. Here and here we're going to show. So here's our light slope. We're going to kind of sketch in, and we're going to lightly draw these on here and think about the fact that the slope at this point is a first-degree line. So the slope at our new point is going to be a second-degree line, which in our case is a curve. So from there to there, we're just going to curve it up and get sort of a hill, so to speak. And our next point is going to be that tiny triangle that crosses the axis that goes from 1.33 to the origin. And we're going to call this our new point E. So our change in moment is going to be the area of that triangle, which is 1/2 times the distance we found of 0.831 times the height of 1.33 kips, and that's going to give us 0.55 kip feet as our new change in moment. So here's 0.55 kip feet, and then we know then that our moment at E is going to be the moment at D plus our new value. So the moment at E is going to be our 66.65 plus 0.55, so we're going to get 67.2 kip feet. And we're going to note that the value of the shear is 0 at point E, which means there's no slope. So that's going to be horizontal right there. And then we can label that, and then we can show the new change in moment that we've added right there. So now we're going to solve for the change in moment between points E and C. So our change in moment from E to C is going to be 1/2 times the 6.67 kips times the length of 8 feet, and then we're going to subtract that minus, so our 5 feet minus 0.83 feet to get our actual base length. So our change in moment here is going to equal to minus 13.9 kip feet. So our new moment is the 67.2 minus our 13.9 to get 53.3 kip feet. So we're going to drop down to about here, and note that the slope is going to be negative based off the slope from the shear diagram. So we have this second degree curve downward, and we're going to take it from up here and we're going to slope down kind of like so. We're going to sketch in our line again, and we're just going to take the curve downward for a negative slope. And next we're going to find the area from point C to B, which is also a trapezoid. So we will find the change in moment here. It's a trapezoid, so the change in moment from C to B is going to be 1/2 times the parallel sides, like we did before, which is going to be negative 14.67 plus a negative 22.67. And that is going to be times the distance between them at 5 feet. And this is going to turn out to be 93.3 kip feet. So for this, we're going to drop down below the axis, down here. So from 53.3 minus 93.3 will put us at negative 40 kip feet. So here's our algebra. The new moment at B is going to be 53.3 minus 93.3. We're going to get 40 kip feet, negative 40. So the slope here is going to be steeper here, so the new curve will be another second degree curve from point C to B. And finally, we'll note that our last area to solve for will be the area of the rectangle from B to the end of the beam. So the change in moment is going to be the area of the rectangle at 8 kips times the length of 5 feet. So our new moment is going to be a positive 40 kip feet. So the moment at the end is a negative 40 plus a positive 40. So we end back up at 0. And here we have a constant value of shear. So we have a constant line from the negative 40 up to 0. And now for later use, here we'll know this is a 1 degree line. So for later use, we can label the max shear and moment that we found based off of our diagram. So for the shear, it's going to be a negative 22.67 kips, and our moment is going to be here at 67.2 kip feet. Our next example will go over techniques on how to solve for the maximum axial shear and bending stress with the values that we found in the last example. For our second example, we want to calculate some stresses in this beam from example 1. We're going to determine the maximum axial shear and bending stress in this beam. So from example 1, we calculated the max shear and the max moment, but we can tell by observation that we only have a 6 kip horizontal reaction at A, which means that we have a constant horizontal force in this beam here. So this means that we can write down our P max as compression of 6 kips, and we want to say that from the shear diagram we know that the maximum shear is just to the left of point B, so that's going to be equal to 22.67 kips. And lastly, our maximum moment was within our span at a value of 67.2 kip feet. From our previous discussion, we looked at the relationships for stresses from strengths and materials to show the axial stress F sub A equal to the force divided by the area. The shear stress, F sub V, in a rectangular beam is 3 times the maximum shear, V, divided by 2 times the area. And lastly, our bending stress is F sub B equal to the maximum moment divided by the section modulus S. Now we're going to go ahead and calculate the section properties, and we are going to refer to table 1B, and this is from the NDS supplement, and that's going to contain the section properties for sawn wood. And then from there, for glulam's, we can look in table 1C, and from there we're going to start by finding the area of the rectangle from the 1B that we mentioned. So we'll take the base times the height, and for an 8 by 20 beam we have the cross section is actually 7.5 inches wide by 19.5 inches deep. So our area is going to be 7.5 inches times the 19.5 inches. And this is going to get us an area of 146.25 inches squared. Now we're going to put this on the other side of the equal sign. 146.25 inches squared. And now we're going to look at the section modulus. This can be found by the moment of inertia I divided by C, which is the distance from the neutral axis, which is at the center. So here it's going to be H over 2. So in our case, it's going to be the 19.5 or 19.5 inches divided by 2. So C is going to be H over 2, which in our case is 19.5 divided by 2, which is going to give us 9.75 inches. So now that we can have this, we can move on to solve for the moment of inertia. For a rectangle, which it uses the equations BH cubed over 12. In this case, the base is 7.5 inches times the height cubed, which is going to be 19.5 inches cubed. And we're going to divide that all over 12. And this is going to give us a moment of inertia of 4,634.4 with units inches to the fourth. And finally, our section modulus is our moment of inertia divided by our C that we found. So 4,634.4 inches to the fourth divided by our 9.75 inches to get our section modulus equal to 475.3 inches cubed. Okay, now that we have our forces and our properties, we can solve for our stresses. Okay, so we said that the axial stress, F sub A, is equal to the force P divided by the area. So we have a 6 kip force, and we want to go ahead and convert it to pounds for PSI. So 6 kips times 1,000 pounds per kip divided by an area of 146.25 inches squared. So our axial stress is going to equal 41.0 psi. And next, for our shear stress, F sub V, this is going to be equal to 3V over 2A, so 3 times our shear max of 22.67 kips. And again, we want to convert this, so we're going to multiply times 1,000 pounds per kip, and this is going to be all over 2 per 1,000 pounds per kip. This is going to be all over 2 times the area of 146.25 inches squared, and this will end up with 232.5 psi. And lastly, our bending stress, F sub B, is equal to our max moment divided by our section modulus. So we have some conversions in here that we're going to have to do. So 67.2 kip feet times the 1,000 pounds per kip, and then that times another 12 inches per foot. So a total of 12,000 inches pounds divided by feet kips, or kip feet, and this is all going to be divided by a section modulus of 475.3 inches cubed, and this will give us our bending stress of 1,696.6 psi. Our next example will go over techniques on how to determine the maximum live load and total load deflection in a loaded beam. Our final example is a deflection problem. We will be using equations from the American Institute of Steel Construction, or the AISC. We have a uniformly loaded beam with a dead load of 1.2 kips per feet and a live load of 1.4 kips per foot over the entire length of 20 feet. Also, we have 3 equally spaced apart points. These are point loads at 5 feet spaced, and they're 8 kip dead load and 10 kip live load. Okay, we also have a 7.5 inch by 19.5 inch wood beam, and we are going to calculate the deflection on this beam. If we were to look in the AISC manual, we'll find that in table 323, case 1, for the uniform load, the deflection equation is equal to 5 times the factored load times the length to the 4th power over 384 times EI. And we can also find the deflection equation for the point loads from table 323, and this is going to be, in this case, for 3 concentrically placed loads in these tables. So in this particular equation we chose from 323, we know that it has a constant little e of 0.05. So our deflection equation for these loads would be 0.05 times P times the length cubed all over EI. So now we can use the equation to add together to find the total deflection. Okay, next we know that previously in example 2 we calculated the moment of inertia of this beam, which was 4,634.3 inches to the 4th, and in this case our length is 20 feet, so we're going to set that equal to 240 inches to convert over, and we typically want all calculations in inches with pounds or kips, so with this we'll use these 2 added deflection equations that we found. Now we're going to do both the live load deflection and the total load deflection. So the live load deflection will be, it's going to be our 5 times our W, which is going to be just our live load, so 1.4 kips per feet. So 5 times 1.4, and then we want to convert, so we're going to multiply that times a 1 foot per 12 inches, so we're going to divide by 12 inches, and our length was 240 inches to the 4th divided by our 384 constant times our elastic modulus of the wood, which was given as 1600 KSI, and then we're going to multiply that by the moment of inertia, which was our 4,634.3 inches to the 4th. That's the deflection equation for the distributed load. Now we're going to add to that the deflection equation of the point loads. So here now we have our little e, so 0.05 times the 10 kip load times the length of 240 inches cubed, and we're going to divide all of that by the elasticity of 1600 KSI times the moment of inertia, 4,634.6 inches to the 4th, and this gives us a total deflection for the live load of 1.61 inches. So similarly, we can do the total load, where the only difference now is that the loads are factored 1.2 times the dead load plus 1.6 times the live. So now we will have that our new loads are going to show for deflection. We have 5 times the new factored load, that's going to be 2.6 kips per foot. And this is going to be times 1/12 or divided by 12 to convert to inches. And we will multiply that by 240 inches to the fourth. This is where we converted our length of 20 feet times 12 inches per foot. And we're going to divide all of that by 384 times 1600 KSI times 4,634.3 inches to the fourth. And we're going to add all of this again to our point deflections, so our concentrated portion, which is 0.05 again, times the factor of 18 kip load, that's our new factored load, times the 240 inch length cubed, all of this divided by 1600 KSI times 4,634.3 inches to the fourth, and that's going to get a total deflection of 2.94 inches. And that is going to be all for our statics and strengths review.